finite formulas, and after that we have studied isometry, types of isometry, some theorems of isometry, and then we have studied covariant derivative and some examples of covariant derivative. Okay, I hope you have solved the examples of the covariant derivative. Now let us go for the next one, that is our third chapter is surface. Now here we are going to study the properties of surfaces with the help of a differential calculus. Okay. So if you remember in the second chapter we have studied the properties of curve. If you take any curve you can find out what is a turning, what is twisting, what is a curvature, what by how much rate it is twisting. That all we can find out with the help of all those Trinit formulas. Okay, these are Shivaji University notes. I have already uploaded this in the Google Classroom so that we can take it and solve your assignments also. So these are nothing but the our uh, Trinit formulas, that is T, N, B, K, 2. T and B forms a frame field at every point of the curve. And you can see here at every, if you are having a curve alpha, then if curvature K is 0, alpha is a straight line. If curvature K is greater than 0 and torsion is 0, this is a plane curve. These we have solved. Now you can go for the next one is K, constant K is greater than 0, torsion is 0, then alpha is a part of a circle with radius 1 upon k. This also we have solved. Now you can solve the next fourth and fifth, that is if constant k is greater than 0 and curvature is non-equal to 0, then k alpha is our circular helix, and if torsion and curvature are such a way that 2 by k is a constant term, then curve alpha is a cylindrical helix. Okay, so you can solve all those examples. So what is a basic thing in the Ferrand apparatus we have studied is, if you're having any curve alpha, you can find out what is a turning, twisting, what is the speed of the curve, what is velocity of the curve, how the curve is twisting, what is the rate of twisting, what is the rate of turning of the curve. These all things you can calculate, and we cannot uh, you don't have to go to that curve, or you don't need to imagine the curve. Just you can use a curve alpha, whatever the given equation, by the given equation itself you can solve and you can say it. That means that is a power of mathematics or differential geometry, that without knowing a curve, without actually seeing the curve, you can say everything about the curve. Okay, so now in the next we have seen isometry and the types of isometry. These are the real life examples of isometry, that if we are walking our first walk, that is our first leg, whatever we are putting, and the third one, they are isometry of each other, and every isometry is a combination of 3 1, and every isometry f can be written as a TC, that is every isometry is written in the form of orthogonal transformation followed by the translation. And we have proved translation is isometry, orthogonal transformation is isometry, as well as rotation is also one isometry. Those who have studied classical mechanics can know that how to find out the rotation matrix. If it is rotation about x, or rotation about y, rotation about z, at that time every time we are getting a different matrix with the cos, sine, and 1 0 0 values. And what is orthogonal matrix, you should know. Orthogonal matrix means, if you are taking any column and multiplication of any column with other column, it should be 0, and the norm of that column should be equal to 1. And the types of isometry we have seen. Now here you can see the matrix of rotation about the z-axis. About the z-axis, hence we are getting the last row is 0 0 1 and the last column is 0 0 1. And we here we can go for the rotation about x-axis also. So first row will be 1 0 0, first column will be 1 0 0, and the corresponding changes. If you are not able to go with this, you can go for the classical mechanics notebook. There we have studied in detail that how to find out the rotation matrix. And then afterwards we have found the orthogonal transformation. What is orthogonal transformation? It preserves the dot product, as well as it is a linear transformation. Okay, so as it is a linear transformation, it should keep the origin to origin its will. This is a property of a linear transformation, that is, it keeps origin as it is. Okay, so after that we have proved orthogonal transformation is isometry. But if isometry wants to be an orthogonal transformation, it should keep origin as it is, because if you see the translation, in a translation every point is moved to some other fixed distance. That is, a translation is a type of a motion, or translation is a function that moves every point to some every point that moves every point in a specified direction with a specified constant vector. Okay, and afterward we have seen some theorem, that is, if S and T are translation, ST is equal to TS is also translation. If G composite F is G is or trans isometry, F is isometry, then composition of isometry is isometry. These things we have studied. Now last time we have studied is a covariant derivative. What is a covariant derivative is? It is also, it is just that we have to find out a derivative of a vector field. Just up to now we have found the derivative of function. Now we have to find out a derivative of a vector field. Derivative of vector field with respect to vector, as well as we have found the derivative of vector field with respect to a vector field. I hope you have solved the example. I have given you some examples to solve in the assignment also, so that you can solve it. So let us go for the next point on, that is calculus on the surface. That is, we are going to study the surfaces in this third chapter. That is, how the surface looks like, what is a just like we are going to see the finite apparatus or the nature of the surfaces. Without actually knowing the surface, we can say everything about the surface. Okay. Now for that, I have shared you one lecture of Jacobian matrix in our Google Classroom. So just see that, so that you can understand why we have introduced the concept of Jacobian. Before knowing the concept of Jacobian, you should know what is a implicit function, what is explicit function, and when you are going to find out a Jacobian matrix, and what is a need to find out the Jacobian matrix. Those who are interested can go for the lecture and you can study that. Now here, what is if you, for the differentiability of a function f, if it is n variable function, then these all derivatives should exist. That is, dou f I by dou xi should exist, so that we can say this Jacobian matrix is going to exist. Okay, now I hope you have studied these regular mappings, and this in our real analysis one, I think third or fourth chapter, where you have studied in some big theorems, where you have studied what is a Jacobian matrix, what is the need of Jacobian matrix, and some theorems in. So I just going to have a regular mapping. What is a regular mapping? A mapping f from En to M. Instead of using En to Am, in the real analysis we have used Rn to Rm. I hope you can go for the real analysis book, real analysis one in the semester first. Last chapter, I think third or fourth chapter, in that you can go Rn to Rm. We have gone through some big theorems. Inverse mapping theorem also. So the mapping f is said to be regular if the Jacobian of f has a rank of n, where n is a dimension of a domain of a function. Okay. The Jacobian matrix of f is given by dou f1 by dou x1, dou f2 by dou x1, dou fm by dou x1, and so on. So here, or in another way, you can write here x. We are going to differentiate with respect to x1 up to so on xn. Or you can change the function. You can keep the function as it is, or you can keep xi as it is. Okay. So this is simply m cross n or n cross m matrix. And if what is the rank of a matrix is said to be R if and only if it contains a non-zero determinant of order R, and every determinant of order R plus 1 is 0. Now I hope everyone knowing that what is a rank of a matrix, everyone say that a number of non-zeros. But what about number of non-zeros? Is everything clear? Can you able to think what is a number of non-zero rows? If suppose I am saying a matrix 1 1 1 1, that is, first row is 1 1 1, second row is also 1 1 1, third row is also 1 1 1. So how many number of non-zero rows I have? 3. So what is the rank of a matrix? It will be 3, but it is not 3, because if you want to calculate the rank of matrix in this case, you have to first eliminate, that is, first you have to apply the operation so that you can reduce the matrix to the echelon form. After reducing the matrix to the echelon form, you can get the rank of that matrix will be 1, that is a single row with entries are 1. Okay, so here also you can see a matrix is said to be of rank R if and only if it contains a non-zero determinant of order R. That is, if you get any determinant, and if it contains a non-determinant of order R, and every determinant of order R plus 1 are 0. And you can verify this in the case of a matrix 3 cross 3 matrix, all entries are 1. So if all entries are 1, every determinant of order 3 cross 3, that is, will be 0. Every determinant of order 2 cross 2 will be 0. Every determinant of order 1 cross 1 is not 0. So hence you can say now the matrix has a rank is 1. You can generalize this concept, that is, if suppose you take any matrix, if suppose the rank of a matrix is 2, every determinant of order greater than 2 will be 0. Okay, so what is a general thing for the rank of a matrix? A matrix is said to be of rank R if it contains a non-zero determinant of order R, and every determinant of a greater order, that is, if non-zero determinant of order 2 you are getting, and every determinant of order 2 plus 1, that is 3, should be 0. If it is 0, then it is good. Otherwise, the rank will be more than 2. Correct? So now let us go for the next one. So we have to first study the coordinate patch in before going to the surfaces and all. What is a coordinate patch? The definition says that let D be the open subset of E2, that is R2 space. Consider the mapping X from D2 to E3. It must satisfy the two conditions. First one is X is 1 1, and second one is X is regular. Okay, what is a coordinate patch? Actually, these things, coordinate patch, proper patch, all these things we are needed to define the surface. To define up to now in our mathematics, we haven't defined what is a surface. Just we are saying any object in the 3D space is a surface. But now in the differential geometry, we are going to define what is a surface. So before going to the definition of surface, we should know what is a coordinate patch. What is a coordinate patch? First, we will define what is a coordinate patch. For that, we must know what is mapping X. X is the mapping from D to E2. What is D? D is any subset of a E2 or R2 space. Okay, so it is in 2D plane. That is it. It is just a mapping from 2D plane to 3D space. Okay, so this, if this x or this function x, if it is going to satisfy the condition of being 1 1 and regular, then it is called a coordinate patch. Okay, so what is the meaning of 1 1? We can say if images are not equal, the pre-images should also not be f of x1 not equal to f of x2, then f of x1 is equal to f of x2, then x1 should be equal to x2. Or in another way, we can say if image x1 x2 are not equal, their images should not be equal. What is the meaning of regularity? If x is said to be regular, if it has a rank of this matrix should be equal to 2. Why the rank should be 2? Because D is a subset of E2. Here also you can see rank of a matrix. We have defined the rank of this matrix will be n. That is a domain. That is said to be a rank n. That is a dimension of our domain space. Okay, mapping F is said to be regular mapping. Here also mapping X from D to E3 space. What is D? D is any subset of E2 space. So what should be the when I say X is a regular map, if it has a Jacobian matrix of rank 2. Why it is 2? Because D is subset of E2 space, where n is a dimension of a domain space. So mapping X is said to be regular if it rank of a matrix, whatever we are getting, Jacobian matrix, the rank of that Jacobian matrix should be equal to dimension of a domain. Rank of a Jacobian matrix should be equal to the dimension of a domain. So here also rank of the Jacobian matrix should be equal to the dimension of a domain. Now let us see how it looks like. That is, first we have a D is a subset of E2 space, and after applying some function x, we will get one object in a 3D space. That means suppose आपके पास एक पत्रा है, आप उसको कुछ ऑपरेशन, दैट मीन्स आप हथौड़ी से उसको बड़ हीट करके हथौड़ी से मार मार के आप उसको एक स्फीयर के फॉर्म में या एक 3D ऑब्जेक्ट जस्ट लाइक अ हाफ स्फीयर, दैट इज सपोज यू हैव अ one rubber sheet. Okay, after stretching that rubber sheet you can convert that rubber sheet in a 3D object just like a hemisphere or half sphere. So this is what a mapping we can call it as some function that is stretching, bending, these type of function you can apply so that any 2D object now we have to convert it into 3D object. But this x, the mapping x should satisfy the condition of being 1 1 as well as condition of being a regular. When the mapping x is said to be regular, if the rank of the Jacobian matrix should be equal to the dimension of a domain. What is the dimension of a domain now? It is 2 because in the R2 space. So the definition of a coordinate path gives that the regular curve with the open interval is now here. If you go for the regular curve, what is a regular curve? Alpha is said to be regular curve. It is a mapping from open interval I to R3 space. That is, open interval I is a subset of D. And what is a regularity condition? Alpha dash of T should not be equals to 0. So instead of that, we are having the condition of a regularity. So here in the next lectures, in the some next lecture, we will prove xu cross xv not equal to 0 gives that the condition of being the regularity. What is xu xv? It means that function x we are going to differentiate with respect to u, and function x we are going to differentiate with respect to u and v. That is, x is some function of u and v. Why it is some function of u and v? Because we have only two parameters here, a u and v. Instead of saying x and y, that it x is x of uv. That means we'll write it as x of uv is equal to some function. Now that the new function may be some u square uv v square, that is in 3D space. Initially we have only two variable u and v, and then we will, after applying a mapping x, we will get a some function or some surface in a 3D space. Okay. So what is a curve? Curve alpha is a function from open interval I to E3 space. What is open interval I? It is any subset of a R. But instead of having any subset of R, we have replaced to I. Now you can imagine this as a curve alpha. So curve alpha is a subset. Curve alpha is a function from open interval I to R3. But instead of having I, we have selected open set D. D is a subset of E2. What was I? I was a subset of R. To some R3. Okay, so we have to apply some things. So that is, आपके पास एक पत्रा है, आप उसको मार मार के एक हथौड़ी से उसको बढ़ोना है. So you can get it in the form of a one 3D object. So here you can take any rubber sheet. So apply the apply the function that you have to just stretch it so that you can get it in the form of a one hemisphere or any 3D object. But what is the condition for that new 3D object? That x should be 1 1 and regularity. What is a regularity condition? In the next lectures, we will study what is a regularity condition. Xu cross xv not equal to 0. So initially, if you go for by the definition, x is said to be regular map if a dimension of Jacobian matrix is should be equal to the dimension of a rank of a Jacobian matrix should be equal to the dimension of a domain. Rank of Jacobian matrix should be equal to the dimension of a domain. In the next lectures, we will study that mapping x will be said to be a regular if xu cross xv not equal to 0. Now you can resemble this on mapping or curve alpha is regular if alpha dash of t is not equal to 0. Here also regularity conditions is going to satisfy with the help of xu cross xv not equal to 0. That is, we are going to differentiate x with respect to u and v as it is a subset of 2D plane. So here we have only subset of alpha is a what is the domain for alpha? is open interval I, which is a subset of R. So hence we are getting only alpha dash of t. But here we are having two dimension. That is, what is a domain for our x is our 2D plane. Okay, that is any subset of 2D plane. So hence we are using the condition xu cross xp not equal to 0. So here we can see that regularity condition gives a smoothness and condition 1 1 avoids the cutting of the plane. 1 1 ensures that every whatever we are getting here in the domain, there should exist image in the codomain. Okay, so this is what a regularity condition gives the smoothness. You can ensure that if alpha dash of t equal to 0 means what, the curve is constant. Here also, if you want to study the regularity condition and use the smoothness, and the condition of 1 1 avoids the cutting of the surface. Why the 1 1 will give you the cutting without cutting in the surface? That means अगर आप if you take any uh, rubber sheet, and if you cut it and then you can make it in the form of a one 3D object, at that time if you go back, that is if you want to check up pre-images, then you cannot get the points that are in the cut part. Okay, so here this regularity condition gives the smoothness, and the condition of 1 1 gives that your plane is not cut, and then x of t, whatever the new object we are getting, is a smooth three-dimensional subset of R3 space. Okay. So next is the definition of a proper patch. So what is a proper patch? Coordinate patch is said to be proper patch. That means x is 1 1 regular, and if x inverse is continuous, that is x inverse is a function from x of t to d. Okay, inverse function we are defining. If it is also continuous, then we say that it is a proper patch. Okay. So in the next lecture, we will solve some